Hi everyone, in this video we're going to look at mainly the basic properties of this Laplace transform and some basic cases and examples. So let me remind you of the definition of Laplace transform. It was this operator. If the function is given, then we're multiplying that function by this integrating factor and integrate from 0 to infinity, if that makes sense. If this is not growing fast, I was wrong about this part, so I'm going to fix that to f here. That's what we mean by that. F goes in there. And this becomes a number. The function becomes a number, but we have this arbitrary positive parameter, so that this has a good chance to converge. But this really came from this idea of differentiating 0 to x. Once this becomes x, like here in this operator, that with this infinity replaced with a main variable x is this operator, it unfolds like this, but as we send that x to infinity, this term approaches 0. If we assume that approaches 0, that allows us this property there. That's the earlier discussion. And the main accomplishment of that is turning this differential first order derivative into a polynomial algebra in S and keeping this initial condition. Then we'll go through an example and explain at the end that some theoretical part of how to interpret this one. But let's focus on examples, properties first. The property will tell us what this really accomplished in here. So that's going to be titled theorem. Now I just stated the first part, which is supposed to be just a copy of this part in here. I realized that there's another typo, but this is supposed to be just a plain Laplace transform operator. So that's what we have. So that's the important part. Everything else kind of falls out of this. But I will just state as a part. This is kind of list of a property rather than stating the rest of the part as a corollary of this one. I'll just state it here. So this first one, it's repeated here. First derivative unfolds, transformed into a polynomial algebra with this part in here. So the following is also useful. If you actually rewrite this one for plain Laplace transform for the y, the original function, then it's going to be this one moves over here and divided by s. So it's going to be derivative y prime plus y0. That's kind of obvious. You solve this one for that LSY. This is going to be useful to compute, deal with the basic example. Number 3 is actually about the second derivative. Of course, when we consider the second derivative, it means the second derivative multiplied by this integrating factor, then this whole thing exists. So suppose we're in that class of functions, then we have the second derivative in here, and that unfolds something like this. Basically, this repeated use of this one 2 times. So here, I'm going to write it as s squared. And the good thing is that we're keeping this shape here, LSY. This second derivative unfolds, still keeping this main term times the polynomial part in s in there. Then next part is the first order of s, and it picks up the original function value. Next part is a constant term of this polynomial in s, is y prime of 0. So the original value, y prime of 0, it involves now these 2 initial values. So let's guess what's going to happen to the third derivative, image of this Laplace transform. The third derivative, it starts from third power, polynomial, and this is the main term, what we want to figure out, or what we basically deal with, and then s squared, that's the second term in the polynomial. It picks up the y0, original function value, and first order, and it picks up y prime, and constant term picks up y double prime. I think that clearly explains how the fourth order and fifth order will look like. But this is basically the property, and with this property we can deduce some of the basic facts about Laplace transform of some basic functions. So let me explain before we state the more properties, or as I put it as a corollary in here. What we have accomplished here, this LS, this Laplace transform, is a linear operator. So if we have linear combination of these guys, y prime, y double prime, y triple prime, where the coefficients are constant, then you can freely manipulate that linear combination through this linear operator, and then you will preserve everything will fall out in this form. So what is the right hand side here? Again, if you look at it, it's all polynomial in S, and this mysterious part is there, but they're all common in this part and here. The common, if we skip that part, this first order, second order, and third order derivative are all written in terms of S and this common Laplace transform term right here. Everything else is a polynomial in S. So that differential algebra with a constant coefficient is turned to a polynomial algebra nicely. So transforming again that differential algebra to the polynomial algebra in S, that's what it has basically accomplished. Using that, we can state some of the basic facts about Laplace transform of elementary functions. So I'm going to state that as a corollary of this one that follows from here. So the first one is, what about Laplace transform of e to the ax? That elementary, the exponential functions. As just an expression, it turns out it's 1 over s minus a. Whatever the a is a constant. Remember, when we consider this Laplace transform, it's always about that infinite integral, and we're considering this one because that infinite integral makes sense. If you consider that one, it's simply the inside the integral turns out is all e to the something by the exponential law. So this part only makes sense when s is greater than equal to, not equal to, and greater than a. So s must be greater than a, not less than or equal to. So then these two things make sense. This exists and that value is this one. So there's this sort of condition there. So next part will be sine and cosine, Laplace transform of sine of ax in there. What's going to happen? Let's think about the integral, and this one is always bounded. It's not affecting the e to the x. So it turns out this is simply s divided by s squared divided by a squared. And number 3, what about, so about that this is supposed to be cosine, comes out the cosine in here, and that's supposed to be sine in here. Sine ax, Laplace transform, is a divided by, running out of room, I hope I get this one. Let me write it over here. Okay, we're over here now. That's perfect. And a over s squared plus a squared. That's e to the x and cosine x. And sine ax we covered. And all these conditions are here. We have a common condition, s should be greater than 0 in here and there. But this one, s should be greater than 0. Maybe I have to clarify it. And this part's not, s can be anything, right? Because you will see that when you look at the integrals. But this part, it comes with s greater than 0. That's part of the definition, so that is the same, but it's not written here. Next thing is that if you have x to the n, where n is positive non-zero integers, then what happened to this one is an n factorial divided by s raised to the n plus 1. So that turns out to be the immediate consequence of this property. Now here's those basic things again. It's difficult to absorb right now, but the basic idea is that there's some consistent rule of transforming the derivative into polynomials, and there's some facts about how some base elementary functions are transforming. So I'm going to consider this example and to show you how these things are play into solving differential equation with the constant coefficients. But before that, I'd like to remind you of the very, very basic differential equation and how it started that kind of solving that kind of problems. So we call that a little recall. So we're going to recall a little bit about solving the following type of an equation. If if I have to figure out the function yx, whose derivative was cosine x. And this is the very small and easiest differential equation you can imagine, and this is the fundamental problem in the integral calculus, integral one variable calculus problem. Now I want you to think about how we solve this problem. Now after you put a little bit of thoughts to this one, I hope you agree that basically the way we have solved it here, we looked at the basic tables of f and f prime, like x to the n, all that, and sine and cosine, and in that in this chart, sine and cosine appeared because they are elementary functions. Its derivative is cosine x and negative sine x. So from that table, you look at, here is my cosine x, this function whose derivative is cosine x probably is a sine x. So we looked at the table and looked through and kind of figured out this basic example happened to be in our list. So that's how we start. So once we have these basic facts, rest of the pod is a substitution rule, an integration by parts, and on and on and on, and learning more technique to realize that some of the complicated looking function can be realized as a derivative of something using the simple and basic facts. That's what you did at the beginning of this integral calculus in terms of the method. So if you think about what we were doing before, it's quite similar to that. Here we have looked at more complicated transformation or transform of a given function called Laplace transform. We have some of the property that is slightly more complicated than integral simple, but we looked at some basic examples and realized that how it transforms. These transcendental functions are transformed to now simple rational functions in here, and this becomes simple rational functions, and this one is also simple rational functions. So like we did for the basic antiderivative problem, and what we're going to do here is that if we have more complicated stuff in the right hand side, can we kind of rewrite doing some of the technique to realize that, hey, that part comes from there, this is showing up in the right hand side, therefore it must have come from there, and stuff like that. So back to this basic antiderivative problem, and you can state the following address this following important question by looking at this table and our observation. We are sure we found one function whose derivative is cosine x. Let me write down here. Here's one function. Just one function we found it here, that whose derivative is a cosine x. And if the question is that are there more functions? And all of you know the trick. I know the more function is a sine x plus 2. If you differentiate that one, you still get this cosine x, and whatever constant you put it in there, you know it's going to be the cosine x. But this explanation does not answer the following question. What if there are more functions out there that is not in this form right now we just described? Is it possible in the whole world of functions, there are functions out there we haven't discovered, but its derivative is really the cosine x, but it is not in this form? It's a meaningful question, and the answer to that is no, and we just move on. They said answer's no, and we don't have to look for it. But in mathematics, if it is the right education you're getting there, you have to think about this type of fundamental question. This is a scientific question. This is what it boils down to, making you thinking. Why is that so? So if you look up your Calculus 1 textbook, and it's somewhere, it must have answered it. If not, throw away the book. That's a bad book. But if it is there, it's a good book. Now, anyway, your calculus, typical calculus textbook, and answers this question. And the way they answer is quite elegant, and it shows a lot of good things about what mathematics is about. So there's this question. I'm going to make this an analogous question to the Laplace transform. So here's a statement about Laplace transform. What this statement is saying is that this is a table we're creating, e to the ax. If you go through the transform, like the derivative, then it's going to be 1 over s minus a. And the question is that, all right, is there something else that goes in there? Is there some function we don't know out there? If you apply the Laplace transform, it still becomes the same function. Is it possible? And we have to address that question when you solve problems. Now finally, here's an example. Let me change the color. It's an example of solving this y double prime plus y equals e to the x. With this initial condition, y 0, y prime 0, both 0. And there are better method to quickly solve this problem, but this is a simple problem and we're using to introduce the idea behind this Laplace transform. So here's the idea. We're going to apply Laplace transform both sides, and this everything here switches, it changes to a different form of a functions. So here's Laplace transform, y double prime y, and here's Laplace transform of e to the x. Now because of the linearity, it's going to split it like this. It's a second derivative plus Laplace transform of the first derivative. The right hand side seems like the basic example we happen to have listed it here. So ls is 1 over this e to the ax. So here little a in this case is a positive 1. Therefore this Laplace transform, this one is 1 over s minus 1. So I'm going to write down 1 over s minus 1 here. So next thing is that we're going to look at the property and how this second derivative unfolds in terms of this zero derivative, and then it's going to really transform everything. So let me show you the second derivative part here. According to that property, if you apply 2 times and you will arrive at here, the second derivative is a second order polynomial. First, second degree term here, first degree term, and constant term. Now we're back here. The left hand side, this part becomes second degree 2, second order, degree 2 term, and there's Laplace transform on the function y, and minus the first order term. Then it picks up this initial value, which we set to 0 here, so that makes everything a bit simple. And then here's a constant term that picks up next order initial value. This was also set to 0 here, but that's only this second derivative order term. So let's look at first order. There's no first order, it is just the Laplace transform on y. If this is first order, you have to go through the first order one as well. So let me write this one over here. All right, and this whole thing is supposed to be 1 over s minus 1. Now if you simplify this whole thing, what you have here is that s squared plus this is Laplace transform on y, there's a 0, and that's Laplace transform on y. So here like this. The left hand side is going to be like this. If these are not 0, think about these are not non-zero, what you're going to have is something purely in terms of s with some constants multiplied. And you can move it over there, and everything else that has this Laplace transform on the same function y can be put together and everything else factored out like this. So I think it's quite convincing that all cases of a constant coefficient case is going to be put into this form. This is Laplace transform times polynomial in S is equal to rational function in S. Everything is all constant in numbers. So if you solve for this guy here, Laplace transform is actually now is 1 divided by this quadratic polynomial multiplied by this polynomial here. All right. So if you can somewhat rewrite this one and realize it, this piece coming from the table and that piece coming from the table and so on. So how do we do that? Is something called a partial fraction decomposition. All right, here's a partial fraction decomposition. There's a different way of writing this one so that it looks more like sum of the following part, the sum of this part, and sum of that part, and sum of that part. Right now it was a product form. Can we write that product form into sums of this type of thing? Because if it's a sum, behave nicely with the linearity of that thing, so we can easily predict where it's coming from. So that's the idea behind it. We're looking at this individual thing, we know where it's coming from. If we can write this one as a sum, then we can predict it easily through this linearity. There are indeed several different methods of doing this partial fraction decomposition. So I'm going to write down some of the things like a standard method. So what we want is a theory says, is a part of the theory says, the right-hand side we're looking at there, which is this part in here, can be written into this form, s squared plus 1 and plus s minus 1 is separated like this. And because it's a quadratic and we have a linear as a general possibility, it's a linear, it has to be constant general possibility. This is possible because these two factors does not have a common factor. If you factor further, this one is s plus I and s minus I in the complex numbers, or you can look at it as an irreducible polynomial with a real coefficient. And this is linear in a real coefficient. So these don't have a common factor over the real polynomials. So in that case, it's possible to split it like this, with this order of the numerator being less than the order of the denominator, if this one is less than the degree 3 down there. So it's complicated. If this whole theoretical conditions and why this one happening, it comes with a lot of conditions. I don't want you to spend too much time on the partial fraction decomposition. Your integral calculus part of your Calc 1 textbook or Calc 1 variable calculus textbook must have this one in there. So this is possible. Then what we do is that you actually expand this one like this, and here s squared plus 1, s minus 1, and you cross multiply as plus b, s minus 1, and c times, writing over here, s squared plus 1. You multiply c there. So if you expand out, that must be just simply 1. So if you do that, so let me write it over here like this, s squared plus 1. So I wrote this part, set it out here. So if you expand it, and you have to collect what is the coefficient of s squared part. S squared is the highest part in there. I picked as a and c as the. So let me rewrite this one. It's very bad. I'm going to rewrite it here. So wrote it here. So we're expanding and this whole thing and thinking about what is this s squared. You can see that this term and that term, these two things are the only term that gives you, these two terms. The only term that gives you s squared here, and that part's s squared. So it must be a plus c. Okay, so let's look at this time s to the first, the s part. Where is this linear terms coming in? There's no s to the first here, so it must be this two term that gives you b, and that two term multiplied each other. That would be negative a. That gives you everything about s. So that must be b minus a here. All right. Then what about constant? Where's the constant part? Constant part, you can see this constant multiply constant. That's the only possibility. And this part with that multiply, that'll give you c. So c minus b must be the case here. That's the constant term. So if you expand on this numerator, it's a quadratic expression like this, and we want to be this one identically equal to this numerator 1. So what's the choice? And we have to set this one equal to 0, and that one equal to 0, and that one equals to 1. So that part is going to be 0, that part is going to be 0, and that part is going to be 1. Although it's going to be like 3 variable and 3 equation, they're kind of isolated nicely, so it is not that complicated. It's not the full 3 by 3 equation or anything. So if it is 0, you can see a is opposite sign to c, and a and b are even equal to each other, and that's the one thing. this one, now that it becomes, c is b plus c minus b is 1, but b is now the same as a because of that. And this I can see a plus c equals 0. Sum is 0, opposite sign. If you subtract, it's 1. So, well, you can solve this system equation however you want, but it turns out it's a is negative 1/2, so that makes a positive, and c is positive 1/2. And c is going to be the opposite sign. A is going to be this. So b is the same as this one. So figure it out. So let me write it over here. And after I delete this part, sorry about that. So let me summarize it here. A and b were both the same. That was negative 1/2, and c was a positive 1/2. So let me separate it like this. And so what we have here is the Laplace transform of y is now separated like this. So where a and b are the same in negative 1/2. So I'm going to factor out negative 1/2 here because they're exactly the same. Then we have s plus 1. These two things are the same factor factored out here. And s squared plus 1. And plus c is also positive 1/2. At the same magnitude is 1 s minus 1. So now this one can be easily separated to the familiar terms that appeared in the table. So they go like this, negative 1/2. To separate it like this, s over s squared plus 1, negative 1/2, and separated 1 over s squared plus 1, and positive 1/2, 1 over s minus 1. So after you decompose it like this, and this was the term that appeared in our table, and this was a term appeared in our table, and this one also. Alright, so I copied that table over here. I hope you can see it's pretty small, but you can see s over s squared plus 1. That looks a lot like this, s over s squared plus 1. If a is 1, then you can have that. So here you can see, alright, if I do ls over negative 1/2, I hope you understand, because the constant, you can just put it anywhere. So that came from this cosine 1 times x. So I'm going to emphasize it at 1 times x. So if you try that, you definitely get this one, negative 1/2 s over s squared plus 1. How about this part? It looks like it's coming exactly from 1, a equals 1, and a squared is 1 there, so that matches exactly this form. So if you try Laplace transform of negative 1/2 of sine 1 times x, is exactly this 1 over negative 1/2, 1 over s squared plus 1. So that's that part. And this one, s minus 1, is exactly where this part's 1, and that came from that part here. So we can say Laplace transform of e to the x is 1 over s minus 1. Sorry about that. I need positive 1/2, so I'm going to insert it there. So here's positive 1/2 of e to the 1 times x will be positive 1/2 as a constant, and e to the x, we notice that it must be 1 over s minus 1. Okay, so we have all the individual terms that showed up here. Therefore, if we write it like this, negative 1/2 cosine x, and the negative 1/2 over there is a sine x, and plus positive 1/2 e to the x is going to be exactly what you see on the right hand side in a shorter form, and it can be written like this, 1 over s squared plus 1 and s minus 1. That's exactly what was right inside. It was the decomposed form in here. So we proved that. We found one function whose Laplace transform is the given function right here. So we found one. Alright, here's a summary of what we have done. Here's the differential equation with a typical initial condition, as simple as possible here. And we have hit both sides of the equation, knowing that existence and uniqueness theorem that there is one. So this is a meaningful equation. Then we unfold this one using the property about what this Laplace transform is doing to the second order equation. And this is one of the basic table. And we isolated the Laplace transform like this, and right hand side is simply the function of s. Now using the partial fraction decomposition, and realize that this decomposes nicely, and all of them are fall into our basic cases. So we looked at the right hand side of here, realize that we found one function whose Laplace transform is this one in here. Now this is the part we have to be careful, and this is the part that student actually never paid attention. But if you're thinking clearly, and don't get offended by this one, but it is true that not many students thinking clearly, and it is one of the most difficult things. It's complicated in the the bottom of this complicated calculation. You easily lose your logic. But here is the situation: we have two functions y and f in here that map to the same thing. And it is, we want to conclude that the y of x we're looking for is f of x. This is what we want to conclude, because under Laplace transform, they became the same function. So let me summarize it here. I have one function, I'm going to call it g1, and went to another one function, hs, under Laplace transform, and another, this invert linear operator. This became another function, but in s, but it was the same. Can we conclude g1 is equal to g2? The answer is no. If you think about the basic linear operator of even the first order and second order linear differential operator, if the kernel is non-zero, if there's a kernel element, if you throw in g1 plus the kernel element, it's not going to affect this hs. So let me explain it here. ls g1, and if I throw in some kernel element, let's say that was f, not f, because I already used f. Well, I'm going to use this weird letter psi x here. So let's say that came from the kernel. Because of the linearity, you know this is going to be lsg1 plus ls Laplace transform of psi here. But because it came from the kernel, that part's a 0, and that becomes exactly the hs in here. So you can clearly see, if this is not non-zero, if the kernel had some non-trivial element function in it, then you can create different function that under this Laplace transform that still goes to hs. So if we know the kernel of Laplace transform, sorry about this, rewrite it. So there's a kernel of Laplace transform is basically 0. There's nothing in there. Well, we have to limit the classes of function, but in our elementary class of function, this is pretty much true. So if we have something like that, and we can conclude, well, there's no kernel involved, therefore there's no way the two different functions map to the same function under the Laplace transform, therefore we conclude the same. So we use this fairly fancy theory and a big theory to conclude that, but this turns out to be true. So if we just assume in this one, and we can conclude these two things are the same. But in your logic, and if you didn't use this fact about the triviality of the kernel of the Laplace transform, and you probably made some mistake in your logic, and it is subtle to discover that. Another way of going about this, close up this problem, not using this fancy big theorem, is that here's a candidate, and let's see if that actually satisfies this equation. So that's one way to close up this argument here. But mainly, these are just introduced as a method of computing things quickly. So why don't we just assume this is the case and use it as a method to solve problems. We already have lots of other methods, and this is another method to help us to determine these coefficients in a fairly efficient way using this partial fraction decomposition. but we need to point it out that there is this thing behind it in here. And in my video somewhere, we will go ahead and see mathematically why this is so. So here's a two-way to conclude. I was saying, let f of x, let yx to be that function, negative 1/2, and cosine x, and sine x, positive half e to the x, and verify the differential equation and the initial condition. It's not writing very well right now. Okay, did that. Or second, we use that theorem, that I listed over there, which is a kernel is 0, so there's no way the possibility any other function that goes to this this function in here. Then you conclude that this is the case. Okay, I'll read that down. So there's two methods, and the fact is that always whatever you found it by inspection and after you do the partial fraction decomposition is actually the answer. Next video, we're gonna actually prove some of those properties and the basic cases.